In this video, we're going to look at positron emission, another way of making a nucleus more stable. This time, we have an unstable nucleus with too many protons. And so here's our option. In the middle, we've got a proton. It's got a positive charge and a mass of about 1. On the top would be the mass. This time, a proton will decay, forming a neutral neutron, still a mass of 1, but no substantial charge. And then we're going to form this little guy. This is your positron. It's the equivalent of like a positive electron. It's a small particle that can be emitted from a nucleus. It has a positive charge, but no substantial mass. So real similar to the last video when we looked at the beta particle. The beta particle was essentially an electron. Its symbol was E, no substantial mass, -1 charge. The positron is very, very similar. It still has the symbol E, but it's almost like a positive electron. It's an equivalent particle, but a positive charge. So if we change a proton into a neutron, and then we emit this positron, the mass number will stay the same. We're forming a neutron, but it has about the same mass as the original proton. But now the atomic number will decrease by 1. Atomic number is the number of protons. So now if I have 1 less proton, the atomic number will go down by 1. All right, so let's look at this example. Here's a cute little picture. I have some carbon, carbon 11, which again, that's not the most stable form of carbon. Carbon 12 would be the most stable and the most abundant. It's the closest to the mass on the periodic table. So here's an isotope of carbon. Its mass is 11. If I look on the periodic table, carbon is number 6. 6 protons. Okay, so let's look at this nucleus, and we'll label some things in here. Let's make these little red dots the protons. So there should be 1, 2, 3, 4, 5, 6 protons. There should be 5 neutrons. If the mass is 11, yep, here they are. 1, 2, 3, 4, and 5. So here's my original atom, not stable. So if I undergo positron emission, we'll release this little positive electron-like particle, and then I'll be left with boron. So we could also write this as boron. Oh, I'll do it in blue. I'll keep it the same color. There you go. Boron. Mass 11, the mass stays the same, but boron is element number 5 on the periodic table. And then I release my little positron. It has no substantial mass, but a positive charge. And the symbol is still kind of like an E electron. Okay, so let's see if this adds up. My particles, then, I should have 1 neutron, 2 neutrons, 3, 4, 5, and 6. Yes. The mass stayed the same, still 11. Protons and neutrons have equivalent mass. But one of the original protons was turned into a neutron. So now the blue particles, if those are my neutrons, I should have an extra. That leaves me then with 5 protons. Protons are positive. 1, 2, 3, 4, 5. Perfect. Mass stayed the same. One of the original protons was turned into a neutron. The atomic number then will go down by 1. So if I look on the periodic table, yep, boron is element number 5. Some more examples. Check these out. Let's say you want to solve these little nuclear equations from positron emission. Now, if they don't tell me that it's positron emission, I can tell by looking at this little particle. The positive electron is the positron. Cute. Okay, so the mass should stay the same. The mass will still be 38. But this time the atomic number will go down by 1. So I should be element 18. I look at element 18 on the periodic table. It should be argon. Oh, not bad. I can handle that. And I can check and make sure everything adds up. 38 plus 0 is 38. And then on the bottom I have 18 plus 1, 19. Not bad. Let's check out this other one, some lanthanum number 57. The mass will stay the same, 125, but the atomic number should go down by 1 to 56. I look on the periodic table, 56 is barium. Barium. So it's this guy, the atomic number, that identifies the element and gives you the symbol. 25 plus 0 is 125 plus 0 is 125. And then on the bottom, 56 plus 1 gives me the original 57 from lanthanum.